Hello everyone, thank you so much for selecting this poster presentation. Let me introduce myself. I'm Cindy Morales from the University of Ferrara in Italy, and in this short video I will show you the results of the recent investigations on the microstructural and mechanical properties of 74 pH laser directed energy depositions. Recently, additive manufacturing has gained a lot of ground against the conventional manufacturing processes due to the wide variety of advantages and the easy way to enable complex component part production by melting only the material at the same time as is deposited on the substrate. With this technique, a wide variety of materials, including carbon, composites, titanium, aluminum, and some other, are satisfactorily processed. However, a specific focus on the selection of the process parameters and the post-fabrication treatments such as heat treatment are important key to produce a good quality part. In this investigation, we are going to focus on the process parameter optimization and the post-fabrication heat treatment behaviors on the 74 pH parts. In the present study, an atomized spherical 74 pH stainless steel powder with the chemical composition exposed in Table 1 were used to produce the samples. This alloy belongs to the martensitic precipitation hardness stainless steel family, which are characterized by a high content of chromium and nickel. With a preliminary study, different sets of process parameters, including power, scanning speed, powder feed rate, and the calculation of laser energy input, were selected in order to fabricate the present specimens. 3 replicas of each single track using the different process parameters were deposited on an IC316L substrate, as we can observe in figure, which were furtherly studied in terms of geometrical features, macro and microstructural through optical microscope, scanning electron microscope, TEM, and microhardness analysis. In addition to this, 3 different post-fabrication heat treatments routes based on the H900 treatment specification for this kind of materials were applied, as we can observe in the first 3 heat treatment conditions, which correspond to the first one to the H900 heat treatment, and the second and the third correspond to variation of the first treatment, but with no solution, and in the case in H3T3, and with a short solution treatment time. In the third case, the heat treatment was directly aged and no solution was applied. Besides that, 2 other long-term aging treatments, which were based on the HT1 and HT3 respectively, were applied to the samples. In this case, 100 hours of aging were applied with and without solution treatment step. After that, the best process parameters individuated different multi-track depositions in two different building directions were deposited, as we can observe in figure. From this, the same characterization techniques and hardness behavior were studied. Besides to perform as well, ball on disc were tested. From the results, as we can observe in these micrographs, the characteristically martensitic matrix with presence of L-DED delta ferrite across the as-built sample, specifically in the part of the grain boundary depositions and interdendritic delta ferrite, were individuated compared with the treated samples, as an example in this case the HT3, that shows a minimum quantity of presence of delta ferrite among the matrix due to the direct aging effect. A strong correlation of the microstructure and the post-treatment effect and the hardness was found, since, as observed in the figure 3 of the hardness plot, the samples with higher values as HT3 and T5 presents the higher values of microhardness, which correspond that these samples don't suffer solubilization or solution treatment of the alloying elements, and no supersaturated solution was formed during the quenching. So, by TEM were individuated the presence of nanometric coarsen strengthening precipitates such as copper-rich nanoparticles and niobium carbides, which were prompt after in the case of the long aging timing. Their presence results in the achievement of the maximum hardness of the sample and in about the 35% of the S-build, as in the case in the HT5, as we can observe. In the case of the HT3, the highest hardness was individuated and correlated with the high presence of the martensitic distribution across the microstructure. Meanwhile, the results of the after the ball-on disc were tested independently of the direction of the building direction show that the samples, as we can observe in figure 6, the samples of the coefficient of friction shows that the H3, which is the green one, show the steadiest behavior during the sliding distance of the test, along with the as-built, which were directly correlated with the presence of the delta ferrite, demonstrated that the microstructure does not influence this value, but however, in terms of the specific wear rate, samples HT3 represents the best wear behavior performing higher microhardness and the best wear resistance in terms of the minimum value of this in this plot. Observing from here that the delta ferrite presence is the main responsible for the improved wear resistance. As conclusions in this study, it was possible to conclude that optimal process parameters are satisfactorily individuated from the 74 pH multi-track deposition once the analysis of the single tracks were performed. However, the different post-fabrication heat treatment were successfully for the increasing of the hardness and the wear behavior of the samples, specifically for those samples HT3 with no solubilization, and for the sample HT5 with direct long-term aging, in which not only the presence of niobium carbides and copper-rich particles help to the increase of the hardness, but also the presence of the delta ferrite helps to the increasement of these properties. However, in order to understand the mechanism and the sequence of precipitation of these particles in the production of these kind of depositions, further analysis are still ongoing. Okay, so thank you so much for your attention. If you have any question or suggestion or doubt, please don't hesitate to contact me, and I will be at your disposal for anything. Thank you so much and have a nice day.